Aloha mai kākou. This is Module 10.1, Climate Change Overview. In this lecture, we will go over what is climate change, why did climate change prior to the Industrial Revolution, what is the greenhouse effect, and what role have volcanoes played in climate change. So first, let's take a look at what is the difference between weather and climate change. Weather refers to short-term atmospheric conditions, defined as a state of the atmosphere at a given time and place with respect to variables such as temperature, moisture, wind, speed and direction, and barometric pressure. For example, on the news for the weather forecast, you may hear about changes in rain, snow, clouds, winds, thunderstorms, sleet, and hail. Next, let's discuss what is climate. Climate refers to longer-term averages, which may or may not be regional or global, and can be thought of as the weather averaged over several decades. Climate is the average weather conditions in a place over a long period of time, say 30 years or more. Generally, Earth's climate is a function of how much solar radiation is received from the sun. For example, if you take a look at this figure, on the right it shows the Earth, and there are 5 major climate zones. You have your tropical zones. This is the hot and humid zone that temperature averages about 64 degrees Fahrenheit. You have a dry zone, so the climate zones are dry because moisture is rapidly evaporated from the air. There's little precipitation. You have temperate zones shown in green, which are at higher latitudes, and they're typically warm and humid in the summer and thunderstorms and mild winters. You have continental in purple. These regions have warm to cool summers and very cold winters. And then you have polar regions shown in the blue. In the polar climate zones, it's extremely cold. Even in the summer, temperatures here never go higher than about 50 degrees Fahrenheit. Climate generally is what you would expect in an area, whereas weather is what you get in that point in time. So next, what is climate change? Climate change is a long-term change in climate, the average weather patterns that have come to define Earth's local, regional, and global climates. Climate change is harder for us to appreciate because the timescales involved are much longer, and the impact of climate change can be less immediate. Examples of climate change include sea level rise, melting of ice sheets and glaciers, shifting seasons, and more. Climate change we will discuss further in this lecture and a second lecture for this week. Next, take a look at this video shown here. For the sake of time, I'm not gonna play it here in this lecture, but you have the link, so you can take a look at it yourself. It'll provide a brief overview of further discussing what is climate change. The material in this video could appear in your quiz and on the final, so please, again, take a look following the link shown here. Prior to the Industrial Revolution, Earth's climate periodically changed between being extremely cold, and these cold periods are known as ice ages, and warm periods known as interglacial periods. These periods of natural climate change were largely due to changes in solar radiation experienced by the Earth. So the amount of solar energy that hit the Earth and then warmed the Earth. Milankovitch cycles. So why did Earth's climate change prior to the Industrial Revolution? One theory is Milankovitch cycles. Milankovitch cycles include the shape of Earth's orbit, also known as eccentricity, the angle that the Earth's axis is tilted with respect to Earth's orbital plane, or its obliquity, and the direction that Earth's spin axis is pointed, also known as precession. These cycles affect the amount of sunlight and therefore energy that Earth absorbs from the sun. They also help us to really understand long-term changes in Earth's climate, including the beginning and end of ice ages throughout Earth's history. So now we're going to go through each of the 3 Milankovitch cycles in more detail, starting with eccentricity. Eccentricity, shown here in this video in the top right hand corner, is Earth's, if you can imagine Earth's annual Huaka'i or trip around the sun. It's not perfectly circular, but it's pretty close. Over time, the pull of gravity from our solar system's 2 largest gas giants, Jupiter and Saturn, caused the shape of Earth's orbit to vary from nearly circular to slightly elliptical, as shown here in this top figure. Eccentricity measures how much the shape of Earth's orbit departs from a perfect circle. These variations affect the distance between the Earth and the Sun. Eccentricity is the reason why our seasons are slightly different lengths, why summers in the northern hemisphere currently are about 4.5 days longer than winters, and springs about 3 days longer than autumns. As eccentricity decreases, the length of our seasons gradually even out because the shape of the orbit is closer to a circle. The difference in the distance between Earth's closest approach to the Sun, which occurs on or about January 3rd each year, and its farthest departure from the Sun is about currently about 5.1 million kilometers, or a variation of 3.4%. That means each January, about 6.8% more incoming solar radiation reaches Earth than it does in July. When Earth's orbit is at its most elliptic, so the furthest from being a circle, about 23% more incoming solar radiation reaches Earth at our planet's closest approach to the Sun each year. Currently, Earth's eccentricity is very slowly decreasing and is approaching its least elliptic or most circular cycle. And these cycles of eccentricity change about every 100,000 years. Next, we're going to talk about axial precession or precession. And you'll see precession shown here in the middle of this video. So, as Earth rotates, it wobbles slightly upon its rotational axis, which you can see here in this figure. This wobble is like a slightly off-center spinning toy top. The wobble is due to tidal forces caused by the gravitational influences of the Sun and the Moon that cause Earth to bulge at the equator, affecting its rotation. The trend in the direction of this wobble relative to fixed positions of stars is known as axial precession. The cycle of axial precession spans about 25,000 years to 26,000 years. Axial precession makes seasonal contrasts more extreme in one hemisphere and less extreme in the other. Currently, when Earth is closest to the Sun, which occurs during winter in the northern hemisphere and summer in the southern hemisphere. This makes the southern hemisphere summers hotter and moderates northern hemisphere seasonal variations. Next, we will talk about obliquity. The angle Earth's axis of rotation is tilted as it travels around the Sun is known as obliquity. Obliquity is why Earth has seasons. Over the last million years, it has varied between 22.1 and 24.5 degrees with respect to Earth's orbital plane. The greater Earth's axial tilt, the more extreme our seasons are, as each hemisphere receives more solar radiation during its summer, when the hemisphere is tilted toward the Sun, and less during the winter when it is tilted away. Larger tilt angles favor periods of deglaciation or warm periods when glaciers retreat or melt. these effects aren't uniformly global. Higher latitudes receive a larger change in total solar radiation than areas closer to the Earth. The cycle for obliquity is about 41,000 years. So every 41,000 years, there are variations in the tilt of the Earth. Next, let's discuss what is the greenhouse effect. The greenhouse effect is a process through which heat is trapped by greenhouse gases in Earth's atmosphere. The greenhouse gases, if you take a look first at this image on the right, the greenhouse gases located in Earth's atmosphere makes Earth much warmer than it would be without an atmosphere. Imagine these gases as a cozy blanket enveloping Earth, helping to maintain a warmer temperature than it would otherwise. If you can imagine now looking at the figure on the left, a greenhouse, a glass house used to grow plants. In a greenhouse, the glass traps the sun's heat, keeping plants within the greenhouse relatively warm even in the winter. The greenhouse effect works much the same way on Earth. Greenhouse gases in the atmosphere, again, they trap heat similar to the glass roof of a greenhouse. Solar energy is observed at Earth's surface, is radiated back into the atmosphere as heat. As the heat makes its way through the atmosphere and back out to space, greenhouse gases absorb much of it, warming the planet. Greenhouse gases consist of carbon dioxide, methane, ozone, nitrous oxide, chlorofluorocarbons, CFCs, and water vapor. Scientists have determined that carbon dioxide plays a crucial role in maintaining the stability of Earth's atmosphere. If carbon dioxide was removed, the terrestrial greenhouse effect would collapse and Earth's surface temperature would drop significantly by about 59 degrees Fahrenheit. Not all greenhouse gases warm the Earth equally. This figure shows the global warming potential of 6 greenhouse gases over a 100-year time scale. The global warming potential measures the relative warming of 1 unit mass of greenhouse gas relative to carbon dioxide. For example, methane is a common gas produced by cows when they fart. Methane has a warming potential value of about 28, meaning that 1 ton of methane has 28 times the warming impact of 1 ton of carbon dioxide over a 100-year time scale. Carbon dioxide, as you can see here in this figure, has a relatively low warming potential, but there's now so much of it in the atmosphere that it causes much of climate's warming. Carbon dioxide accounts for about 82% of greenhouse gas emissions. Furthermore, carbon dioxide molecules remain in the atmosphere for a long time. After 100 years, about 40% of the carbon dioxide that is in the atmosphere today will still persist. Fluorinated gases such as hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and sulfur hexafluoride, SF6, are human-made gases that are used in refrigerants, air conditioners, foams, and aerosols like hair care products or certain cleaning products. Fluorinated gases may only account for 3% of the greenhouse gas emissions, but they may be as much as 23,000 times stronger than carbon dioxide. They pose a threat to the atmosphere also because they are not a natural component of it, and they have long residence times. It can take a really long time, as shown here on the right hand side. It can take hundreds, if not thousands of years for these fluorinated gases to be removed from the atmosphere. Carbon dioxide, as mentioned previously, is the most closely monitored gas because it is the primary greenhouse gas emitted through human activities. It currently accounts for the greatest portion of warming associated with human activities, and is particularly long-lived in Earth's climate system. These graphs show monthly mean carbon dioxide measured at Mauna Loa Observatory, Hawaii. That's right, the longest record of atmospheric CO2 is recorded here in Hawaii. Mauna Loa was chosen as a long-term monitoring site due to its remote location, far from continents, and its lack of vegetation, which is important because plants consume carbon dioxide during the day due to photosynthesis. The carbon dioxide data on Mauna Loa constitutes the longest record of direct measurements of carbon dioxide in the atmosphere. And these measurements were started in 1958. If you take a look here at these two graphs, you will see that the graph here on the left shows the measurements of CO2 for the last 5 completed years on Mauna Loa, plus the record of the most current year. The full record of combined data between what's recorded by NOAA and an oceanographic institute known as Scripps is shown on the right. The red lines and symbols represent the monthly mean values centered on the middle of each month. The black lines and symbols represent the same after correction for the average seasonal cycle. CO2 levels in Earth's atmosphere have passed 420 parts per million, compared to pre-industrial levels of 280 parts per million, an increase of over 50%. Next, we will discuss what the role of volcanoes has been in climate change. Volcanoes can impact climate change. During major explosive eruptions, huge amounts of volcanic gas, aerosol droplets, and ash are injected into the stratosphere, as shown here in this figure on the right. Injected ash falls rapidly from the stratosphere. Most of it is removed within several weeks to days and has little impact on climate change. But volcanic gases like sulfur dioxide can cause global cooling, while volcanic carbon dioxide, a greenhouse gas, has the potential to promote global warming. So again, CO2 and sulfur dioxide, carbon dioxide and sulfur dioxide are the biggest players when it comes to volcanoes. The most significant climate impacts come from volcanic injections into the stratosphere. The most significant climate impacts from volcanic injections into the stratosphere come from the conversion of sulfur dioxide into sulfuric acid, which condenses rapidly in the stratosphere to form fine sulfate aerosols, shown here by this plume. The aerosols increase the reflection of radiation from the sun back into space. So that's shown here by these arrows. This results in the cooling of Earth's lower atmosphere and troposphere. Several eruptions during the past century have caused a decline in the average temperature at the Earth's surface of up to half a degree for periods of 1 to 3 years. The climatic eruption of Mount Pinatubo on June 15, 1991 was one of the largest eruptions of the 20th century and injected 20 million tons of sulfur dioxide into the stratosphere at an altitude of more than 20 miles. The Pinatubo cloud was the largest sulfur dioxide cloud ever observed in the stratosphere since the beginning of observations by satellites in 1971. It caused what is believed to be the largest aerosol disturbance of the stratosphere in the 20th century. Consequently, it was a standout in climate impact and cooled the Earth's surface for 3 years, following the eruption by as much as 1.3 degrees Fahrenheit at the height of the impact. We also mentioned that Earth's volcanoes emit CO2 and could potentially warm the planet. So the question here is, do the Earth's volcanoes emit more CO2 than human activities at present? To put into perspective, while volcanic eruptions do contribute to an increase in atmospheric CO2, human activities release an amount of CO2 equivalent to what a Mount St. Helens-sized eruption produces every 2.5 hours, and a Mount Pinatubo-sized eruption twice daily. The most significant eruptions come from supervolcanoes like Yellowstone or Mount Toba, which erupt very rarely, about every 100,000 to 200,000 years or more. Yet the total annual CO2 emissions from human activities are akin to one or more Yellowstone-sized super eruptions occurring every year. So, published scientific estimates of all global carbon dioxide emissions for all volcanoes and submarine volcanoes is about, we would say, 0.13 to 0.44 gigatons per year. The 35 gigaton projected anthropogenic carbon dioxide emission for 2010, which is about 13 years old for now, is about 80 to 270 times larger than the max and minimum annual global volcanic carbon dioxide emission estimates. So, no, Earth's volcanoes do not emit more carbon dioxide than human activities. Alright, well, that is all for our first lecture, for lecture 10.1. This is a reminder for you to all complete quiz 10.1, which is due in a week from now. It is due on Wednesday at 8 a.m. Please complete your quizzes on time, as we move forward, there will be no late quizzes accepted.